Okay, so today we're moving into section 6.2. Same thing, I'm going to split this up into part 1 and part 2. We're going to get into some graphing. So we're going to look at, this is new vocabulary here, a linear relation. It's a pattern made by a set of points that lies in a straight line. So I just put an example here. You'll notice that this pattern forms a straight line. You can see the word line in there. And we can use, there's a number of ways we can represent linear relations. We can represent them numerically, so through a table of values. We can represent them algebraically, so through an equation, and we can represent them graphically. So that's going to be our focus today. We're going to look to see how we can connect these representations of a linear relation. There's two ways to determine if you are in fact dealing with a straight line or a pattern that is linear. Number one, you can just look at the graph and it should make a straight line. So you can look at it visually. And number two, you can look at the table of values, and both the x and y values will go up or down by the same amount. Okay, so what we'll do, we've got in example 1 here, I've got 4 examples, and we want to determine whether or not they are linear relations. The first one, so what we do, we look at our x values. So our x values are going up by 1, and we look at our y values. They're going up by, well, going up by 3. This one here only goes up by 1. So we would say that no, this is not a linear relation, because also if we were to graph it, we would not get a straight line. So example number 1 is not a linear relation. The x values have to increase by the same amount, and the y values have to increase or decrease by the same amount. So number 2, let's look at our x values. They're going up by 2, and our y values here are going up by 4. Okay, so our x values are going up or down by the same amount. They're all going up by 2, and our y values are going up or down by the same amount. They're going up by 4, so we could say that yes, this is a linear relation. If we were to graph it, we would get a straight line. Third example, so let's look at our x values. Looks like we are decreasing by 2, and for our y values, so going up by 5, going up by 5, going up by 10. So our x values are linear, but our y values, you'll notice there it goes up by different values, so it's not a linear relation. And then the fourth example, it's a graph, and just by looking at it, we can see that it does not form a straight line. So that's not a linear relation either. Okay, moving on to example 2. So this is where we're going to tie in the equation, a graph, a table of values, because they all represent a linear relation. So create a table of values and a graph for this equation here. So step 1 is to make a table of values. I'm just going to abbreviate it TOV. So when we make a table of values, we always have x on the left-hand side, it's the independent variable, and y on the right-hand side, it's the dependent variable. If we look to this equation here, we don't have x and y, but hopefully by now you would know that this one is y and the s represents the x. So I'll use the letter S here for x and the letter R for y. And when we make a table of values, we use our x values of -2, -1, 0, 1, and 2. And then what we want to do is plug it into the equation and solve for y. So r equals -3s plus 4. So if I plug in -2 for x, or for s, my r value or y value ends up being 6 plus 4, so 10. Okay, if I plug in -1 for my s value, my y value, my x value ends up being 7. So we've had lots of practice at this. I'm not going to keep rewriting this out. If I plug in 0 here, I would get 4. If I plug in 1 here, so 1 times -3 plus 4 is 1. And if I plug in 2 for my x value, I would get a value of -2. Okay, so we practiced that last day as well. So I've got my table of values, and now what I want to do is graph the coordinates. So these here are the coordinates. -2 and 10 is a coordinate. This one here, -1 and 7 is a coordinate, and so forth. Okay, so I'm going to graph these coordinates, and keep in mind the first one is x and the second coordinate is the y value. So you can pause the video and try that on your own. That's review. Okay, so you can double check that you have graphed the correct coordinates. So step 1 was to make a table of values, and step 2 was to graph the coordinates. Okay, and what you can do is take a ruler, connect them, and make sure that you put arrows on both ends to show that this would continue on. Like we could have kept going. What would happen when x equals 3, 4, etc. So these arrows become very important to show that it's not just from one set of points to the other, that it does in fact represent a linear relation. Okay, on the second page, example 3, create a graph and a linear equation to represent the table of values. So here we have our table of values, here we have our graph, and we need to come up with our linear equation. Okay, so these are all ways to represent linear relations. Okay, so how do we come up with the equation? We had practice with that the previous week. So we start off with this equation here. Y equals something x plus something. This value here is the y value when x equals 0. So when x equals 0, y equals -1. Okay, and then we look at the table of values. What do we have to do with the x to turn it into the y, knowing that we have to subtract 1. That just gives us a bit of a hint. So it looks like we have to multiply the x values by 3. So 3 times 3 is 9, and then take away 1. So there's our equation. Y equals 3x minus 1. And now what we want to do is graph the equation. So same thing, I'll pause the video, I'll get you to graph it, connect the dots using a ruler. Okay, so you can double check your graph. What I did was I took the table of values, and each x and y becomes a set of coordinates. So -3, -10, and I went and graphed that point, and I did that for all of them. And then I'm going to take a ruler, connect them, and make sure that I put arrows on either end. We'll learn later on in the lesson that we don't always connect the dots. It depends on the equation. Okay, example 4. Determine the linear equation. So determine the equation of the line that models this graph. So I want to come up with an equation. I think some of you might be able to read off from here. That's great. But what I would recommend is step 1, make a table of values. And so we have -2 and 8 as a set of coordinates, -1 and 4, 0 and 0. This one here is 1 and -4. And the last one is 2 and -8. And then from the table of values, you can come up with the equation. So our equation, the skeleton is y equals something x plus something, and this one here, what is the y value when x equals 0? It's 0. And what do I have to do to the x value to turn it into the y value? And it looks like I have to multiply it by -4. So we have y equals -4x plus 0. So that's the y-intercept. And if you look at the graph, that's where the graph crosses the y-axis, right? What's the y value when x equals 0? We don't have to add in the plus 0, so we can even just leave it as -4x. Okay, next example is the graph shows a relationship between cost in dollars and the mass in kilograms of pears. Part A, what is the linear equation? So first thing that we will do is make a table of values. And it's always x on the left and y on the right. And it looks like our x values are mass. We could use the letter M if we wanted, and they're in kilograms. And our y-axis is cost. So we could use the letter C, and it is in dollars. So reading from the graph here, 0 and 0, when the mass is 0, the cost is 0. When the mass is 1 kilogram, the cost is $2, and so forth. So when the cost is $2, when the mass is $2, the cost is 4. When the mass is $3, the cost is 6. And when the mass is 4 kilograms, I think I messed up my words there a bit, sorry. When the mass is 4 kilograms, the cost is $8. Okay, so now let's come up with the equation. What's the linear equation? So y equals something x plus something. this one here is the y value when x equals 0. So it's 0 again. And it looks like to turn the x value into the y value, I just multiply it by 2. So y equals 2x. And I could replace the x and the y with the other letters, like x actually represents the mass and y actually represents the cost. So C equals 2m. And I find that when you're using these formulas, sometimes it's easier to know exactly what x is and exactly what y is. Okay, on the third page there, how much could you buy for $5? So what you can do is you can just go to the graph, and $5 is right here. So you could just read right off the graph. So it looks like you can buy, for $5, you can buy 2.5 kilograms. So you could, method 1, look at graph. So 2.5 kg. And method 2, you could use that formula. So C equals 2m, and we want to plug in $5 for the cost. So 5 equals 2m, and solve for m. So divide both sides by 2, and we get m equals 2.5 kilograms. So either way, okay. Is it appropriate to identify values on this graph that are between or beyond the plotted points? So what that means, and that will be our last topic there, is when I look at this graph, is it possible to calculate the weight of numbers in between the dots, right? So can you have points between the ones on your graph? Could I have a mass of 1.5 kilograms or 1.75 kilograms? And if you know, like grocery stores, for example, use a scale, and they would calculate the cost for 2.7 kilograms, for example. So, yes? Because, for example, you can find the weight of 2.5 kilograms. You can find the weight of all the numbers, basically. And that moves us into our last topic, connecting the dots. So we have the variables, like on the x-axis and the y-axis, can either be discrete or continuous. A discrete variable is a set of values that only consist of certain numbers. So you can only have certain numbers. So we use just dots for this. So discrete with dots. And a continuous variable is a set of values, and you can have all of the numbers in that interval. So for this, I like to say we connect the dots. And you'll notice connect starts with a C and continuous variable starts with a C. Just a quick way to remember it. So let's look at these examples here. Here we have hotel reservations, number of rooms, and total hotel costs. So the question is, can you have half a room, right? So if I was to make a graph, I have these dots, would I be able to connect them using a line? And I would if I could have numbers in between. So could I have 2.3 rooms, for example? And the answer is no. So this is an example of a discrete relationship. You can't have half a room. You can only have 2, 4, 6, 8, etc. Question B, number of stories and the height of the building. So can you have half a story, right? The answer is no, that you can't. You either have 1 story or 2 stories or 3 stories. So this also is an example of a discrete relationship. We would not connect the dots. Question C, here we have years, and here we have height of a tree. So could we find the height of a tree for 1.5 years or 1.6 years? So this would be an example of a continuous relationship. D, time taken to complete a 100-meter sprint. For time, we can have points in between the ones because time can be broken up. So this would be continuous. And question E, shoe size. So with shoe size, you either get a size 4, a 4.5, a 5, a 5.5, a 6, etc. So that you can't have values in between those. So shoe size is considered discrete. And height of students. So height, when you take the height of somebody, you can have a continuous graph. So you'll get some practice at continuous versus discrete as well. So that's the lesson. You can start the workbook questions and the worksheet that's been attached.